Okay, but after this range means D is somewhat greater than the 8 or 8.5, we will have the this region, and in this region actually instead of increasing the output voltage, the output voltage decreases and goes to the zero. So practically we cannot use the boost converter in the range of say duty of the 0.85. That is also again depends on the means what is the your inductor resistance and all these things, but a rough range is from 0.85 to 1. We cannot use the boost converter to boost the output voltage. So that is a just rough consideration, because we will end up in this region where the output voltage is decreasing actually. So that was the boost converter. Then we derived the different equation for the boost converter, I max, I mean, and all that kind of L minimum, L value. So all that we derived, C value we derived. Then we some of the non-ideality consideration we consider. So that is the equivalent series resistance, ESR. So by having the ESR, the voltage ripple, whatever we consider, so that will not depends only on the C value, but it will depends on the current through the RC and what is the value of RC. So depending on that, we can have the uh, boost converter this thing ripple, output ripple. Okay, so this was the derivation where we saw that by considering non-ideality, you will get the voltage range a decreasing mode. Then we solved one equation or the design. Then I gave you the one homework. So first we will complete this homework just as we completed the boost converter, and then we cover the remaining just recap, and then we will go for the new parts. So the uh, design problem was that a boost converter is required to have the output voltage of 8 volt. Means VO is equal to 8 volt is given. Okay, VO is equal to 8 volt. Then and supply a load current of 1 ampere. Load current means IO is given 1 ampere. So IO is 1 ampere. The input voltage varies from 2.7 to 4.2 volt. So this is the different case as compared to the previous our problems. So here the input voltage is varying between this one. Even if you take the battery, so battery when we say the 9 volt or the 1.5 volt or 3 volt, so it will not always remains to that voltage. When it is fully charged, it will remains to the 3 volt or the 9 volt, but once it gets start discharging, so the voltage will reduces. So similarly there will not be many sources will be there which will varies the voltage, and from that voltage we want a constant voltage of 8 volt actually. So that was the requirement. And for that, what we have to do, we have to adjust the duty every time. So when 2.7 is there, from 2.7 we have to get the 8. So for that, whatever duty is required, that we have to adjust. And when 4.2 volt input is there, from that, if I want to 8 volt, so whatever duty is required, so I have to adjust that duty. And that will be done by the control circuit. So we have the some control circuit which will take care of this and adjust the duty such that the output voltage will remain always to the 8 volt. Here they have asked select the switching frequency, determine the value of the inductor such that the variation in inductor current is no more than the 40% of the average inductor current. So 40% of average inductor current is the limit to have the ripple in the output. Current for all operating condition. Determine the value of an ideal capacitor. So first they ask the ideal capacitor value such that the output voltage ripple is no more than the 2%. So the output voltage ripple they ask to keep in the 2%, and for that the ideal capacitor, and determine the maximum capacitor equivalent series resistance for the 2%. So once you calculate the C, they ask the you have to calculate the maximum equivalent series resistance such that the your ripple should not exceed also the 2%. So that was the problem. So here the problem, while solving the problem, we have the voltage range, input voltage range. So what we have to do, we have to calculate the everything to the all extreme case, means lower extreme case and highest extreme case. And whatever highest and what are there, so that we can take. So the same thing in the solution has done. So first they have chosen the 200 kilohertz for the switching frequency. So it is arbitrarily they have chosen the 200 kilohertz. Then here they have written the circuit must be analyzed for the both input voltage extreme to determine the worst case condition. We have to take the worst case condition. So for that we have to analyze for the both the cases, and whichever is the worst case that we can take for the design purpose. Now first for Vs is equal to 2.7, which is the lowest voltage. So if it is 2.7, so D will be calculated as 1 minus Vs by Vo, which is nothing but 1 minus 2.7 by 8, and the output is 0. Duty is the 0.663. So for this duty, if I calculate the average current IL, so we have the equation as Vo IO divided by Vs. Vo is 8 volt constant, IO is 1 ampere given, Vs is 2.7, so it will give us the 2.96 ampere. Now delta they have mentioned the 40%. So 40% of the IL. So if I take the 40% of 2.96, it will give us the 1.1 ampere. So delta IL should be within the 1.19 ampere if the input voltage is 2.7. So with that, if I calculate the L, so I will get the L value as the 7.5 microhenry. And the calculating the L is the formula is VST in divided by delta IL by F. So F is 200 kilohertz, delta IL we have calculated, Vs is given, varies between 2.7, and the duty just now we have calculated. With that we will get the 7.5 microhenry. Now the same thing we have to calculate L for the input voltage equal to the 4.2. Okay, so considering the Vs as a 2.5 to 4.2, we have to again calculate the duty. Then IL calculated by VO by Vs. Now Vs is 4.2 here. Here also the Vs has taken as a 4.2. For that duty is 0.475, and the IL is coming as a 1.9 ampere. Okay, and the variation in inductor current for this case is delta IL. Again, that is the 0.4% of the IL. So for that case, if we calculate, so it is coming 0.762 ampere. And if we calculate L value for this, then again the same formula. If we put all this value, you will get the 13.1 ampere. So in previous case, it was 7.5 microhenry. Sorry, and here it is a 13.1 microhenry. So whatever the worst case, so this is the worst case design thing. So we have to take the value of this. So the inductor must be 13.1 microhenry to satisfy the specification for the range of input voltage. Because we have to satisfy this 0.4 or the 40% of the IL to a whole range. So if I take the lower value, so for at 2.7 volt input voltage, it is satisfying, but it will not satisfy when the input voltage is 4.2. So that's why whatever the worst case is there, that we have to take. So the inductor is 13.1 microhenry. Now, maximum value of D gives the minimum capacitance, because see, the capacitance is directly proportional. So the whatever D is higher value, so you will get the highest value of C as the worst case value, which is the minimum capacitance required actually. Okay, so that's why D is taken as highest, which was the at the 2.7 volt condition. So that is taken, and other values like a R is not given, but output voltage and current is given. So VO by IO is the R. Delta VO by VO is given. It is a 2%. They have asked, and switching frequency is 20 kilohertz. With that, you will get the 20.7 microfarad. Now one more thing they have asked is the ESR, and the maximum ESR is determined from the equation using a, so if you go for the some previous equation for the ESR, see, so ESR is, sorry, delta IC by RC. So whatever maximum IC is there, and the delta IC is nothing but here coming as a delta I actually. So for maximum delta I, you will get the maximum value of the ESR. So that's why they have considered as a, the maximum ESR is determined from the using the maximum peak to peak variation in the capacitor current. Whenever there is a maximum capacitor current, so that time the maximum ESR value you will get, or the maximum ripple you will get. The peak to peak variation in capacitor current is same as the maximum inductor current. So it is actually delta I IC, which is equal to I max of inductor, IL max actually. So we have to calculate the IL max. Now from which value we have to calculate the IL max? So the average inductor current we have seen, see here we got the average inductor current as 2.96, and in second case we got it as a 1.990. So these are the two values, 2.96 and 1.90. But 2.96 we have calculated at 2.7 volt. It is looking as a higher value at the 2.7 volt. But actually this we have calculated for the L value of 7.45 microhenry. But now we have considered as a 13.1 microfarad Henry as a capacitance, inductance value. So at 2.7 volt, again you have to calculate the average value by considering the inductance value of which you got for the 4.2, or which is the worst case. So what we have to do, delta IL Vs d L by F. Now Vs we have considered the 2.7 here, but the inductance value which was the worst, that we have considered. Okay, but if I take the 7.2, I will get the this value. But actually now we are not considering the inductance value as a 7.2, but we are considering the inductance value as a 13.1. So that value we have to put, and then we have to calculate the delta IL, and that delta IL will give is giving the value of 0.683 ampere. So previously it was, if you consider, it was 0.762 ampere, but now it came to the 0.683 ampere. Okay, so what we did, first we calculated with the different input voltages, L value we have calculated, and whichever L value worst case was there, so that we have chosen. Now for that L value, we have to calculate, the L value will not change for the 2.7 or the 4.2, whatever the input voltage is there. So now we have fixed the L value now, depending on whichever worst case is there. And for that L value, we again calculated the delta IL for the Vs is equal to 2.7 also. And that using that values, so by using that values, we calculated the IL max by taking the equation as a IL plus delta IL by 2 and IL plus delta IL by 2 for the both, and we calculated that values, and we are getting the 3.30 ampere as the maximum value here again when there is a 2.7 volt input voltage. So this we have to consider for the calculation of the ESR, which is equal to 3.3 ampere. So calculating the ESR, the formula is delta IC by RC, but delta IC is nothing but IL max. So I will take it as a 3.3, which is the worst case, and which has given as a 2% of the output voltage, which is nothing but equals to the 0.16. So I will equate that to the 0.16. With that, I will get the RC value as a 0.16 divided by 3.3 ampere, which is 48 milliohm. So we have to choose the capacitor which will have the ISR lower than the 48 milliohm. If it is greater than the 48 milliohm, so this criteria, that is the 2% of the output voltage ripple, so that we will not able to meet. So that's why we have to choose the capacitor. We have to go into the capacitor data sheet, check the ESR values, and if it is greater than the 48 milliohm, so we cannot choose that one. We have to choose the capacitor with a ESR value which is lower than the 40 milliohm. Suppose in case a whatever capacitance is there, for that value you are getting not getting this milliohm or this ESR value, then what we have to do? We have to take the half of the value of the capacitance and connect two capacitance in the parallel. So here what is happening? If you go for the basics, the capacitance is getting added here. So here I have taken the C by 2 value, and again here C by 2. So capacitance is getting added here because in capacitor, if it is in the series, sorry, in parallel, they will get added, and resistor, whatever ESR are there, so that are getting the half of the value actually, if they are equal. Okay, so you'll get the equivalent of this if you see. So it will be giving the RC by 2, whatever RC value of each is there, and C value is C. So like that you have to connect in the parallel capacitor to get the this value. Clear?
Yes, sir.
Yeah. Okay, then I will just have the recap for the buck boost converter. So again, buck boost converter is the structure is like that. When switch is closed, the current will flow in this direction, and when switch is open, the current will flow in this direction. And depending on the switch is open and closed, if we derive the equation, we'll get the equation this one. Vo is equal to minus Vs into bracket D divided by 1 minus D. So we have seen that if D is less than 0.5, you will get the output voltage which is less than the Vs. If it is 0.5, you will get the same output voltage as input voltage. And if it is greater than the 0.5, you will get the higher voltage than the input voltage. The other one buck boost, then other equations we derived, and then we went for the Chook converter. So where again it is again a buck boost converter, but it will have the two inductors and two capacitors in the circuit. And by switching on these switches, we will get the similar output equation, but with a filtered input and output capability. Okay, so that was the yesterday's recap. Now we will have the some of the I will not go now any new topology or the new converter thing, but just whatever we have learned. So where how the practical reliability is there, or in practical how they have used. So some of the practical concepts I am trying to have here. So one of the practical aspect is the interlude. Interlude means what? Uh, we connect the we connect one or two two or more converters in the parallel. So if we connect in the parallel, and if we adjust their operations, then we can get the lower ripple as compared to the a single converter will have. So with that we will get the lower ripple, and it is called as the interleaving of the converter. One example of the interleaving is the buck interleaving. So you can see this is one buck converter. So this is the switch, this is the diode which is connected to the ground, and here inductor L1, and you will have the output. The second first buck converter again is connected here. So you can see this is the second switch, second diode, and the second inductor which is connected to the again the same output. So you can see the plus point is here and plus input plus point is here and output plus point is here, which are the common to the both the converters. Also the negative point is the ground point they have shown. So these are also common. So you can say here two converters are connected in the parallel. Okay. But one trick is used such that this switch and this switch, they will not operate at the same time. Means whenever there is this switch is there and this switch is there, so they will operate at a 180-degree phase shifted. 180-degree phase shift means what? So if we have the time of t here, okay, so one switch suppose turning on here, so this is the duty d for the first switch. So instead of turning on the second switch also at this instant, what I will do, I will switch on the second switch, this switch, after the 180 degree of the this time period. 180 degree time period of means what? T by 2. So suppose T by 2 is here somewhere. So what will happen? The second switch will be turned on at this position. Okay. Instead of turning on the second switch also at this position, it will be turned on at the this position. So what will advantages you will get for this? If you see the inductor current is like this, it is rising here and it is falling for the this period. Now for this, what is happening? The inductor current will start rising here and the falling here. And it was the previously off, so it was the falling in this region. So what is happening? So the rising and falling slopes have adjusted to each other. So the same thing is shown here. You can see here. So S1 is closer in this position and S2 is closer in this position. So with that, rising period of each has changed. They have shifted by the 180 degree. Now the output current will be what? Our this current plus this current. So if we add both this, so what is happening? You can see. So this is the lower, this is rising here, here. So if you see one cycle of any switch, so this was the rising period and this was the falling period. So this was the total period for the one switch. But now in this one total period, you are getting the two period. So the frequency has increased here. And the ripple also, if you see here the positive is there and here the negative is there or the falling is there, which will cancel to each other. And what will happen? You will get the lower ripple as compared to the one converter is giving. So at the output, you will have the lower ripple as compared to the individual this thing. One more thing which I can show when duty is equal to 0.5. So what will happen with a duty is equal to 0.5? Just I will show exactly 0.5. We will see. So this is the T, 2T, and this is the T by 2, and this is the 3T by 2. Okay, so two cycles we will take. Now one switch is closing for the 50% of the duty. That is the 0.5. Hello. Okay. And second switch I said as I said, it will be turning on after the 180 degree. So this first switch duty is here. Second switch duty is here. And they are equal, 0.5. Now what will happen? Now if I draw the current for the first switch, so this is the rising, this is the falling. Again, this is the rising, this is the falling. Okay. Now for second switch, this is the falling up to this, and this is the rising. Again, this is the falling, and this is the rising. Means at point, if we add this, what you will get always, this is twice of the this value, twice of this IL, which I have shown. Why it is happening? See, the here it is peak, highest peak, I max, here I mean. They are coming at the same time. So if we add this, you will get the this twice of the this value. Similarly for here also, your peaks are here, so this point and this point. So they will get cancelled to each other, and you will get the constant, a very much constant current at the output. Okay, so at point 0.5 duty, you will get the exactly constant current. There are no ripple. For other duty, you will get the lower ripple as compared to the individual, and at point 0.5, you will get the no ripple in the output. So the ripples are getting cancelled to each other. So that is the advantages of having the we can say the interleaving, and generally the interleaving will be done in case of the when we are connecting in the parallel, and of course the devices and everything are increasing, but the current ratings are getting by the half here, because whole current we have to pass through the this both converters. So half of the current ratings switches are and inductors, everything is used here. So like that we can have the interleaving, and whenever there is a interleaving, so the formula is we have to interleave with a angle of 360 divided by n. So interleaving should be the 360 divided by n, because interleaving will not be between the two. It can be between the 3, 4, 5, whatever number of converters are required. So here two are there. So 360 divided by 2, 180 degree, which we did. If three converters are there, then the 360 by 3. So we have to interleave by with a 120 degree phase angle. Okay, 120 degree. If it is 4, then 90 degree. So like that, whatever number of interleavings are there, with that you can have the that much phase difference between the all the converters. Got the concept of interleaving? Or any clarity is required for this? Anyone? Hello? Hello? Am I audible?
Yes, sir.
Yes, sir.
Okay.
Yes,
Okay.
sir. Yes, sir. You are audible.
Okay. 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 So that was the concept of interleaving. Uh, so whenever we require the high power, that time generally we go for the interleaving of all the converters, and this applies for the all the converters. So interleaving of the all the converters, we have to switch on the switch by the formula 360 divided by n. So if it is n is 2, then we can interleave by 180 degree, then 3 120 degree interleaving, all that kind of thing to get the lower ripple at the output. Then second one practical thing is that the non-ideality of the switches. So till now we have considered the all switches as the ideal. So but in practice there will not be any ideal switch. Whatever we have, the MOSFETs, IGBTs, thyristor or everything, so or the diode also, it will have the some voltage drop across the that switch. So you will not get the exact what formula we have used. So I can show that for the buck converter. So for buck converter, we studied that whenever this switch is closed, we have considered this as a short circuit. There is no voltage drop. And when switch is closed, we consider that the VL, the voltage across this inductor is as VS minus directly VO, because this was the path for the current when switch was closed. And here we have not considered any drop. But actually in practice there is a some drop across this switch, even though it is a close. So if I say the drop is across this switch as a VQ, then the voltage across inductor will not be Vs minus Vo, but it will be Vs minus Vo minus VQ. So this drop also has to be subtracted from the in the equation for the VL. Similarly, when switch is closed, sorry, when switch is open, then we have to, our path will be, just a minute. Okay. So now second case is the when switch is open. So this path is already open, so there will not be any drop, but that time the diode is freewheeling. So this is the path for the current. And again, that time also we have considered this diode as a short circuit. There will not be any voltage drop, but in actual practice, and the inductor voltage was that time equals to the minus VO. But in actual practice, it has the some drop, which is equal to the VD, we can say, VD voltage drop, diode voltage drop, it is called as on time voltage drop. So that range between the 0.2 volt to almost for the power diodes, it is go up to the 2 volt or the 2.5 volt. So that much drop will be there across the diode. So in that case, our VL will be minus VO by VD. So if I add this inductor voltage when switch is on and switch is off and equate to the zero, so what I will get? Uh, Vs minus VO, which is the voltage when the switch is closed, into D, the time for which or the duty for which the switch is closed, and minus VO by VD when the switch is open, that time the VL, and the time or the duty for which the switch is open. If I equate that to the zero, I will get the output voltage as VO is equal to VSD minus VQD minus VD into 1 minus D. So if we compare our previous equation, which was the VO is equal to VS by VS into D, and this equation, so there is a large gap, you can say. So what is happening? So there is a some drop is happening across the your switch for the duty time T. Also the drop across the diode for the 1 minus D duty. So with that, what you can say, the whatever output voltage is there, so that will be the lower than the idle case, because this drop is getting subtracted from the which you got the at the early, in initial case or the idle case. So these are the some things which we have to consider while designing the practical converters. So the practical converter design, we have to consider all these things. So if I want to have the 3 volt at the output, then whatever duty is coming, suppose my input voltage, I will take the simple example. So my output voltage is 5, required is 5 volt, and input voltage is 10 volt. So in that case, ideally duty should be the zero point 0.5. But if I have the zero point 0.5 only, uh, this this term will come as a 5 volt, but this drop, if I subtract, so at the output I will not get the exact 5 volt. So I have to increase the duty more than the zero point 0.5 to get the 5 volt actually. So in that case, may your duty will come as a 5.2 or 5.3 value, and with that duty you will get the output voltage as 5 volt with a 10 volt input. Okay. So I will just ask from this actually, you can have the some practical design of the all this atom. So try to have the take one simple converter and try to design the converter, not only in the pen and paper, but also in the hardware part also. So that will give the more insight in the your in the DC-DC converter actually. So try to just take one example of the, you will have the power supplies, DC power supply. So there you can get the any voltage. Say I will have the 10 voltage input power supply, and I will want to get the 5 volt. So you can get the source. Then from that you design the inductor, then design the capacitor, then you can consider the switch, diode, and all that kind of thing. And switching on this switch, you will require the PWM. So PWM generation, you can just search. You will get the different options. From that, you can have the one simple option is the you can use the what is called as the actually I forgot the name. Simple name was the actually oscillator. Some oscillator is there which will use the different frequency PWM. So there are some ICs where you can have the PWM generation inside. So that kind of things also you can explore. So that will give us the more idea for that one, and try to have the one design of the buck or boost converter. So once you
So
do
can
by
we
hand,
simulate this in a PCM?
yeah, you can simulate also. So that is also good idea. So you can try to simulate also. You can simulate into the MATLAB. You can simulate into the we can say you can try to simulate in the LT Spice actually. Why I am saying the LT Spice? So this software is free of cost. Okay, it is a open source software. Okay, and there you can have the many manufacturer will use the this module this switch with a spice module actually. Okay, so that spice module you directly can use into the LT Spice. So actual characteristics, actual drop and everything will be considered in the your design actually. Or in MATLAB also you have the facility to add the drop and switching characteristics and everything to get that one, and try to analyze the how switching is happen, what kind of things are happening. Inductor also you take the inductor with series one resistor, small resistor. Capacitor also you have to take the with a ESR value, all that kind of you, and try to change the values and see the how the output voltage and everything is getting changed here.
Yes, sir.
So that kind of things also you can do in the simulation. So you will get the feel of how the other things are affecting on the your designs actually. Okay. Okay. So I just added this part as a because it is in your syllabus. So that's why I just have the overview of this. So actually, this buck boost and buck boost are the some basics converter topologies. But generally, when you study the DC-DC converter or any syllabus, if you see, so they will call it as a choppers, and they will divide that into the different types actually. So like a first quadrant chopper, second quadrant chopper, third quadrant chopper, fourth quadrant chopper, like that. Also they called as a chopper A, chopper B, type A, type B, all that kind of view. So as a syllabus, I am just giving the overview for this type of the choppers. So type A chopper, or it is also called as the first quadrant chopper. It is a simple a buck converter actually. So if we consider the first quadrant chopper, it is a buck converter, switch, diode, and inductor. They have not shown, but in practical things, there will be the inductor and the capacitor actually. So first, how the quadrant will be decided. So depending on the output voltage and output current actually. So if output voltage and output current, if it is always positive, you cannot have the negative, then you will operating in the first quadrant. If output voltage is always positive and you can have the output current which is negative also, so in this direction also, then that will be the second quadrant. Similarly, if output voltage is negative and output current also negative, that will be the third quadrant. And if output voltage is negative and output current is positive, then it will be the fourth quadrant. So like that, different chopper quadrants are there. So in first quadrant means it will be having the only positive output and positive output voltage and positive output current. So that is our simple buck converter, which will give us the only first quadrant operation. Similarly, for the second quadrant operation, actually the second quadrant operation will require the some kind of source in the load as well. So this is the LE load. So the one example of LE load is the our motors. So the motors will have the inductive load plus it will have the back EMF. So the back EMF will be generated in the motor. So that kind of load is the LE load. And if we have that kind of load, we can have the uh, reverse output current as well. Means the current can flow in this direction as well. Uh, so for that, it is called as the type B or the second quadrant chopper. Then type C, type C chopper is the two quadrant operation. Means it can operate in the first quadrant as well as the second quadrant. And again, as for the second quadrant, we require some source at the output. So we can say again the motor load. So if I want to run the motor, I can operate in the first quadrant. And if I want to make the braking of the motor, so that time instead of wasting the power in the braking, I can take that power to the and send it to the source. So that will operate it in the second quadrant. So for that, we can use the two quadrant choppers or the type C choppers, where you can see actually it is a like a buck converter only, but instead of only here only switch was there. So now instead of switch, the diode also is used here, and here it is again instead of only diode, the switch is also used. So what will happen? When it operates in this direction, it will act as a buck converter, and when it is operating in this direction, it will act as a boost converter actually. So buck boost operation in the same this thing, but actually it is a either buck or boost in one direction, not the both. In one direction it is not giving the both. In one direction either it will give the buck or the boost. In this direction it is buck, in this direction it is a boost. It is called as the synchronous buck converter or the synchronous boost converter. It is not called as the buck boost, because buck boost means in one same direction you have to get the bucking as well as the boosting operation. But this type of the converter gives the either buck in this direction or the boost in this direction, and this will be operated as a type C chopper or called as a type C chopper and can operate in the two quadrants. Then comes the type D chopper, where you will have the two quadrant operation, but the quadrant operations are the first quadrant and the fourth quadrant actually. And generally this type of the chopper is used for the getting the this this I miss this quadrant operations. And last one is the type C. So in type C we will have the four quadrant operation actually. Means it can operate in all the quadrants. So you will get the output voltage positive as well as the negative, as well as the output current as a positive as well as the negative. So the all four quadrant operation you will get with the this type. Clear? This choppers. Just I have given the overview. What are the chopper? Means actually they have did the category only. So four quadrant operation can be achieved by the different DC-DC converter as well. So, but if it is operating in the four quadrant, so it is called as the type E chopper or the four quadrant chopper. Uh, okay, so with this, means actually I have tried to complete means in the time span whatever I can cover, so that I have tried to complete. I will go for the some of the questions which some student asked for the electric vehicle charging system. How is it? So that I am going to cover. But before that, if you have any question, then we can address it first, and then we will go for that one. If no question, then just we can have the 5 minutes break. Then we can start the uh, actually means how the DC-DC converters or the other converters are used for the electrical vehicle charging system. Is it okay?
Yes, sir.
Yeah.
Yes, sir.
Okay, then we will have the 5 to 7 minutes break. We will come back at uh, 8:07. Okay. I am back. Just let me know when we should start. Vishal sir, should I start?
Yes, sir. You can start, sir.
Okay, thank you. I think everyone back. I will just share my screen again. Just let me know once you are able to see my screen.
Yes, sir.
Okay.
Yes, sir.
Okay. So we just went through the some of the DC-DC converter topologies, but in actually, if you see, there are plenty of the DC-DC converter. There exist plenty of the DC-DC converter topologies. So they are majorly classified into the two parts. One is the isolated converter and non-isolated converter. Non-isolated means there is no isolation between the input and the output. Whatever input and output is there. So if you see their ground or the common path, negative path is common for both, either for positive or negative. Okay. So in that case, it is called as the non-isolated. Isolation means electrically isolation. We need to give the electrical isolation. How we can give the electrical isolation in the any of the converter or anything? As an electrical engineer, we know the isolation we can give by with a very high impedance. Okay, so if I have the very high impedance something, so that will also gives the isolation between the input and output. But with that high impedance, we will not able to transfer any power from the input side to the output side. So that is the one isolation. Second isolation again, it's a kind of uh, we can say the high impedance isolation only by having the some switch here. So if I open the switch here and here, so they are again completely open, but that is also isolation. But again, we will not able to transfer the power. If I want to transfer the power from the input to output, still I have to have the isolation, electrical isolation between the input and output. The way is the use of transformer. So transformer is the one a very good innovation which has happened in our electrical field, which can use the very good isolation between the from the input to the output. So here what is happening when you are supplying the voltage at the input side, so they are magnetically coupled but electrically isolated. So we can transfer the power from the input to the output without having the electrical coupling. So there is only magnetic coupling, and with that magnetic coupling we can have the input to the output isolation, right? So you must have studied the transformer complete subject, and in that all these things you have already covered. So the transformer is a good innovation which in the electrical field which can give the uh, isolation between the electrical terminals actually. Okay, so same thing. So if we want to have the this kind of isolation to transfer the power from input to the output, so there we can use the transformer for the isolation, and that if we are using the transformer in the converter, so it is called as the isolated converters. But here we are talking about the DC-DC converter, and how we will get the how can we use the transformer in the DC-DC converter. So for that, generally what will be done? So whatever DC supply is there, so we will have the some power electronics. So here we have the constant DC suppose or the some DC supply. We have some power electronics which will convert this DC to a very high frequency AC. So it will convert to the AC with a very high frequency, and then it will be given to the high frequency transformer. Okay. So again, it will be coupled with a high frequency transformer, and the secondary again will have the some power electronics to convert to the DC. So this is the type where we use the isolated converter. Okay. So this is called as the isolated converter. Again, in isolated converter, there are two types. One is called as the unidirectional and other one is the bidirectional. Unidirectional means power flows from the input to the output only. Bidirectional means power can flow from the input to the output as well as the output to the input. Okay. So this type of the DC-DC converters is called as the bidirectional converter. And if the power is only flowing in the one direction, then it is called as the unidirectional. Now in unidirectional category, there are again different converter topologies which are used for the with a isolated converter. That is, some of the examples are the flyback converter, half bridge converter, push pull converter, full bridge converter, forward converter, three phase bridge converter. So these are the some of the types which are the unidirectional but with a isolated converter. The flyback converter is very popular in the uh, our like is if you are using the adapters or the SMPS, if you have heard, SMPS is the switched mode power supplies which are used in the computers. Okay, so all this kind of power supplies use the flyback converter actually. And one more thing, good thing is that by using this transformer, we can get the isolation. Also, we can get the step up or step down at the a different means a very high voltage level. Suppose I have the 500 volt input and I want a 5 volt output. So if you calculate the duty for this with a buck converter, so it will have the very low duty requirement. So where it will be difficult to operate it for that lower duty. But in this case, by adjusting the turns ratio, we can get the sum of the step up or step down at this transformer as well. And remaining we can get from the converter control. So with that also we can get the very high step or step down also with the isolated converter. So all these are there. In bidirectional, there are some well-known converters are the three-phase DAB. DAB is nothing but dual active bridge. So dual active bridge, three-phase dual active bridge, half bridge dual active bridge, hybrid dual active bridge, full bridge dual active bridge. These are the some example actually. There are many more actually. Okay. So these are the some isolated converter topologies. Non-isolated, which we already seen, that is the buck converter, boost converter, buck boost converter, and choke converter. So these are the a broader classification for the converters, and for the EV application, we are generally going for the this one isolated. There is a requirement for the means for the small EV, there is no requirement of this isolation, but for the EV cars or the trucks and everything are coming, there is requirement of the isolation, and for that we have to go for the isolated DC-DC converters only. So there we cannot use the buck boost, all that kind, but we have to use these converters. Clear? Okay, so as some student ask for the what are the different converters used in the EV
Yes, sir.
application. So first, just I have given the brief about the how the EV chargers are there, electric vehicle chargers are there. So they broadly classified into the three categories: level 1, level 2, and level 3. Level 1 category is the voltage of 120 volt single phase AC. If you are charging the electric vehicle with a single phase uh, AC supply, which is available at our home, 120 volt is available in actually in US, not in our India. In India, we will have the 230 volt. Okay, 230 volt AC. So we fall into the this category, type 2 category. For type 1 category, generally it is available in the US. So for that, they have defined as a level 1 thing. So they can charge from the AC supply, and the ampere current rating will be from 12 ampere to the 16 ampere, and charging load will be the between the 1.4 to 1.9 kilowatt. And charge times for the vehicle, we can get the 3.5 million miles of the range per hour. In 1 hour, we can charge the battery so that we can run the vehicle for the 3 to 5 miles actually. So that is one category. Second category is the AC level 2, which is the 208 volt to the 240 volt single phase volt AC again. Current rating is 12 ampere to 80 ampere, typically 32 ampere, and charging is varies between the 2 volt to the 19.2 volt. Sorry, not volt, kilowatt, and typically 7 kilowatt is there. And with that, we can charge the 10 to 20 miles per hour actually. Okay. Third category comes. So, but you are saying I have shown the level 1 and level 2 as a AC supply directly. So how you will charge the battery? Battery will require the DC. So in that case, the charger will be available in the EV itself. So which will convert that AC supply to the DC, and then it will charge to the battery. So that will be available in the EV itself. Okay. So every vehicle or the electric vehicle will come with the either with a is level 2 charger or the level 1 charger, which is an onboard charger actually. Level 3 category for the charger is the DC fast charging, where the charger is available at the outside and it is directly connecting to the battery here. So there is no intermediate charger available in the EV. So the charger itself available in the your outside box, and that directly charge the this one. As it is a outside, so you can charge with a very high power as well, because if we want to high power charging at the inside this one, so it will becomes the weight, increase the weight of the vehicle, and once you increase the vehicle, so that much average also get reduces, because that much load also has to carry the vehicle along the journey na. So that's why the battery power will be used to carry that load as well. So generally no one will use the high power charger in the electrical vehicle which is on board. High power chargers will be available outside only. Okay. So Siemens is the one of the company which is providing this charger. So we are not giving any onboard charger, but we are giving the offboard charger. It is called as the offboard charger, which is the power is varies between the almost from start from the 50 kilowatt and up to the now the chargers are up to the 500 kilowatt. So this much power range charges we supply in the Siemens, and these are the offboard chargers. So again, for this, the voltage range is 208 to the 480 volt. 480 generally available in the US again. Three-phase AC supplies will be the input. Current will be the below 125 ampere, and charging load will be the less than 90 kilowatt. But now up to 500 kilowatt is also coming in the same category actually. So it is revised now. And in with this, we can charge the 80% charge in 20 to 30 minutes. So if I have the vehicle which has the average of say 200 miles, so 80% of 200 miles I can charge into the 20 to 30 minutes actually. Okay, so these are the level 1, level 2 and level 3 type of the chargers required for the electric vehicle. Now this charger will have the AC to DC converter as well as the DC-DC converters. And what type of the DC-DC converters? So that I will show you in the next slides. Okay, so here again I have shown the overall structure of the our electric vehicle charging systems. So you can see if there is a only onboard charger available, that is the level 1 and level 2. So we will get the AC supply, and which is directly given to the some rectifier which will convert AC supply to the DC, and there will be the DC-DC converter because we want a variable DC to charge the battery. So that's why we require the variable DC, and so that will be done by using the DC-DC converter. But it will be again the most of the cases it will be the isolated DC-DC converter. Okay, so that will charge the battery. So this is the onboard charger. Then the offboard charger, what it will do, the charger will be available outside only. It will take the AC power, convert to the DC, and again the control DC by using the DC-DC converter, and that will directly charge to the battery. So that is the offboard charger. So you can see here how the overall structure will be there in the vehicle. So vehicle will have the one onboard charger, which will be connected to the AC supply here. That will convert AC to DC, and that DC to DC, that DC supply is given to the DC-DC converter, which will charge the battery. Also, there is one more DC to AC inverter to give the power from the battery to the motor, because to run the vehicle we have to give the supply to the motor. So once motor start rotating, so you can have the get the directly to the vehicle will move. So that's why one more converter is required, that is the DC to AC converter to power up the motor. Also, there are some other electronics load like a AC, then display, and all other kinds of thing, window up, down, and all that automatic windows and everything, which again also require the DC supply. But that is the low voltage DC supply is required. So there again one DC-DC converter will be there, which will take the power from the battery like this, and it will give to the electronic load. Okay. So this is the overall inside that you will have the this converters. So this is the low power DC-DC converter, high power AC to DC converter. High means in that means actually for the onboard charger overall rating will be the lower, but in that again it is again the kilowatt. Suppose I have the onboard charger of 5 kilowatt. Okay, so in that also this DC-DC converter will be a few watt only, say 500 watt only. So this will be the lower because our load, AC load and other loads are to a lower power as compared to the motor load. Motor load is the highest load. So that's why it will be the 500 watt only. So this is the 500 watt DC-DC converter. One example just I am giving. Then the DC to AC as per the motor rating, it may be the 2 kilowatt motor is there. Then the DC to AC converter of 2 kilowatt will be there, or 2 kVA. And to charge the battery again we will require the 5 kilowatt if you have the 5 kVA or the 5 kWh battery rating. Okay, so that is overall inside one. Outside, which is the offboard charger, there we will have the AC, three-phase AC supply input, AC to DC converter, and a large DC-DC converter which directly charge the battery here. Okay, so just you can see the penetration of the power electronics in everywhere. This is just one example. Electric vehicle is the one application actually. So there also you can see how the power electronics is used. So like that, nowadays you cannot find any electrical devices which don't use the power electronics now. Everywhere we will have the power electronics. So that much integration of power electronics has happened into the electrical field actually. Okay. So just after giving the overview, I will go for the converters. So this is one example of the converter, onboard converter actually it is. So onboard charger is there where you can see the AC supply is taken and it is charging to the battery. Okay. Just one question here. How many DC-DC converter you can see here? Anyone? DC-DC converter I am asking, which we have learned now. Anyone. Let it be the wrong. You can answer it.
Two.
Two. Okay. Anyone else? Anyone else have the other answer? Okay.
I think everyone should answer.
Yeah. Everyone should
Let
answer
it be
actually.
any number, any number. That is the answer only.
This is not an exam, so you can answer anything what you feel actually. Okay, let it be. But two is the correct answer. So by see, you can see here. First of all, the AC supply is taken. So there is some filtering is required at the input side to should not the noise transfer from the AC to DC or the from the AC to battery side or from battery side to the AC side. So that's why some filter is required. After that filter, here it is used a simple diode rectifiers, full bridge diode rectifiers, so which will convert from this AC to the DC. Now coming here, so this part you can see. So this is called as the power factor correction, PFC, but actually it is a boost converter. You can see this is the inductor, this is the switch, this is the diode. So the boost converter can act to correct the power factor of the input. So even though it is not giving the isolation, so that's why it is not used for the DC-DC application. But here it is used to improve the power factor. So the power for to maintain our power quality, we have to maintain the power factor. So the unity is the always power factor requirement for the any source. So if we want to put that one, so there should be from the diode, from diode rectifier, you will not get the unity power factor. So your power factor will be very poor in case of the diode rectifier. Okay. But if I use the boost converter and if I do the some control here, then I can have the unity power factor with a diode rectifier and this boost converter. So that is the one more beauty of the this boost converter actually. So here this is the one DC-DC converter is used, but not for the DC-DC application, but to have the power factor correction. Okay. Then this second part, which is isolated DC-DC converter, you can see here. So what is happening? Here four switches are there, like a H bridge only. I don't know, you have learned the inverter part. So where you have the simple H bridge inverter. So the same H bridge type of the is used, which I already said. So this will convert here the DC supply is there. So this DC supply is converted into a very high frequency AC here, very high frequency AC like this. Okay, and that will be given to the transformer. Then there will be the magnetic isolation, and the secondary of transformer again uses the diode rectifier to rectify the output. So once you rectify, you will get the again DC supply here. So from here to here, you will converting fixed DC and to the controlled DC. I will say the controlled DC here. So whatever voltage, whatever current I want, I will get the here to charge the battery. Okay, so here we have used the two DC-DC converter. One is the boost converter to correct the power factor, and one is the isolated DC-DC converter. It is called as the, actually whatever shown here, here it is a LLC converter actually, because it is uses this L and C. That's why it is called as the LLC converter. What are the advantages of LLC converter and all that kind of things? It will be completely a different lecture actually. So I will not go in deeper of that LLC converter. But of course, there are, as I said, many topologies are there. So the LLC is the one of the good topology which will give the very high efficiency for the DC-DC converter. So that's why it is generally used for the where we require the isolated DC-DC converters. I hope that clarifies the how the charger will be looks like in the converter, in the onboard charger, and some of the onboard charger example I have given. So in some, for a very like a two-wheeler and all these things, so there is no isolation is required. So there directly this type of the onboard chargers are also used, where we will have the AC supply diode rectifier and the boost converter, which will act for the power factor correction as well as the it will use the DC supply here. Some of the interleaving also done. You can see this is the interleaving is done here for some of the chargers. It is a boost converter again, but with a interleaving. Then this is the full bridge LLC resonant converter. Sorry, it is not a full bridge. Actually, it is a half bridge because we have the only one leg. So this is the full bridge actually. So this is the full bridge. This is the half bridge LLC. Then this is one more this thing. So it is called as the phase shifted full bridge. Phase shifted full bridge. Then we also have the some modified phase shifted full bridge with a center tap rectifier stage. So these are the some topologies. These are the sorry, up to here non-isolated, and from here to here isolated. So these are the some converter topologies. DC-DC. Here I have shown the only DC-DC converter topologies which are used in the onboard chargers. Clear? Then offboard charger. Of course, offboard chargers will require the higher power and the input also the 3 phase. So many times what will be done on the input side, 3 phase AC inverters are used. So that can be the 2 level. So it is a 2 level, and some multi-level converters are also used. That is, this converter topology is a 3 level actually. It is a 3 level and it is a 2 level. The converter, this converter itself, it will take the power factor correction things. So there is no separate requirement of any DC-DC converter to have the power factor correction. Then in that case, here we will have the again different converter topologies like a DAB, dual active bridge, that can be single phase, 3 phase dual active bridge. And again here we can connect this at the output side. We can connect either in the series or parallel. So you can see these are connected in the parallel to get the higher voltage. So two are connected in the parallel. So even though if I want to output voltage up to the 1000 volt, so this converter will operate at up to the 500 volt only, and this converter again operate at up to the 500 volt only, and this I have connected in the series to get the up to 1000 volt. And if I connect in parallel, so what will happen? The current will get double here. So these are connected in the parallel here in this side. So the current here half of the current, here half of the current, and you will get the twice of the current here. So to get the higher voltage, we generally connect in the series. The converters are connected in the series, and to get the higher current, we generally connect the converters in the parallel. Right? Any question?
No, sir.
Okay, again, these are the some different converter topologies used for the offboard charger. Here mostly there is no use of non-isolated DC-DC converter. For the offboard charger, always it will be used the isolated DC-DC converters. So this is one half bridge configuration, then full bridge configuration, three-phase configuration, half bridge. So these are the unidirectional. You can see at the secondary side only diodes are there. So the power will flow in this direction only. There will not be power flow from this side to this side because diode will conduct in only one direction. So there is no chance to transfer power from the output to the input. These are the some bidirectional converters which uses the switches on the output side as well. So as the switches are there, so they can conduct in the reverse direction also, and you will get the bidirectional operation. So these are the half bridge DAB, dual active bridge, full bridge DAB, dual active bridge, three phase DAB, dual active bridge. Clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So you can see just we are considering the DC-DC converter part of the power electronics. Still, it is a so vast topic. So only one point is the converter topology. Again, one converter topology. After that, you can for the same converter, you can have the different switching frequency, and depending on that switching frequency, you will have the different losses, then different we can say the filters requirement and all that kind of thing. So you will have the when you have the design, means you want to design anything, so you have the plenty of the options. Is whether I can use the unidirectional or the bidirectional, isolated, non-isolated, buck, boost as per our requirement. Also for the switch point of view, whether I have go with the IGBT, whether I will go for the MOSFETs. Again, for the IGBT or the MOSFET, again I can use the SI MOSFET, SIC MOSFET, GAN MOSFET. Which MOSFET I have to use? So that criteria again comes. Again, the current rating wise, which one is good, which switching frequency I have to use, with that what magnetics I can get. All that kind of things are different criteria are comes in the picture when you start the designing any of the converter. So this is the one just the DC-DC converter. Like that, power electronics have the DC to AC converter, DC-DC converter, AC to DC converter. All that kind of the converters are there, and in all these things, different topologies, different devices, different semiconductor material, all unidirectional, bidirectional, all that things are coming actually. So as you and if you see the if I want to analyze the operation of the any converter, then I require the all the basics of the inductor, capacitor, and all that kind of thing. Also to control these devices, I require the control topology. Also, as I said, these switches will not have the idle switches. There will be the some drop, and if there is a some drop, so okay, some drop voltage is there, and some current flowing through this. So there will be the losses of V into I. So whatever current is there, and whatever voltage drop is across the any switch is there, so that much loss will be there. So this loss, what will happen? This loss will get converted into the heat. That heat has to be dissipated. So to get dissipate, we require the heat sink to dissipate that thing. So again, we require the mechanical things to dissipate that heat. So like that, if we consider the power electronics to design a one good converter, we will require the knowledge of all the field actually. First of all, power electronics itself is a vast thing, and in that also to design any power electronics device, we again requires the other streams knowledge as well. And if you start doing this one now, this is a very interesting subject, I can say. Power electronics, don't take it as a miss boring subject. You take it as a challenging or the we can say interesting subject. You will find a very good miss inside in this power electronics, and you will miss enjoy the learning of this power electronics. And as if you learn this power electronics, you have the plenty of option in the market. Everywhere power electronics is getting used, so this knowledge will not get waste actually. So please, this is the request. I know uh, I have given the lecture, but in this lecture, whatever I have given, that is also not possible to get grasp everything. You require to go back, do again the same thing again from yourself. Try to do this different things as well. Then only you will grasp the whatever knowledge I have transferred to you. Otherwise, there is no use of whatever lectures I have given actually. So that's all for my lectures actually. Uh, Different again, I don't want to go on any different topics and confuse you again more and more. So that's why I thought I will stop here, and I will have some time so I can take the question answer if you have anything, or anything if you want to clarify, not only the DC-DC converter, other any power electronics thing, anything you want to clarify, we can have that discussion.
Okay, platform is open for question answer. Uh, Students are encouraged to ask their queries to sir. It's not limited to what sir has covered. You have also, if you have any question related to domain of power electronics, you can ask. Maybe it is dealing with your capstone project, or any doubt that you have, you can ask.
Yes, please. And one more thing, if you try to do some hardware project in power electronics, and if you require any help, so you can reach out me, where I can help you. Simulation also, if you are doing some simulation, if you get some really a good we can say the problem or the some doubt, then you can reach out to me. I will try to help you.
For simulation purpose, right now we are using
Am I
PCM.
audible?
Yeah, if you are using the PSPICE, then there also you can
Hello?
directly use the PSPICE models. So the switch models, spice models will be available. So that also you can use in the PSPICE actually.
Okay.
Yeah. Yeah.
Yeah.
Someone was saying something.
Yes.
Hello, sir. Am I
Ah,
audible,
yes.
sir?
Yes. You are audible.
Sir, I was having one problem, sir. Uh, I have done some simulations about the buck converters and proteins, but when actually I'm implementing it on breadboard or something, it fails to give the
You,
proper output
uh,
as expected.
sorry, Yash, your sound is not clear. Can you just repeat your question?
So the question was like that. I'm doing the simulations on proteins, but what
Okay.
happens it is when I'm it practically on breadboard or something, it fails to give the desired output. What may be the probable reason for it?
You are doing the simulation in Proteus,
Yes, sir.
and there you are getting the output voltage
Yes, the required ones. But when I'm
required one.
practically implementing them with some sort of connection loss or something, I can see their own. But then to the output voltage which I am desired I want to get, it's getting below that too much.
Miss, actually, in that problem statement, I cannot say like that why it is not giving the output to the your hardware, because whatever you are getting in the simulation, and if you are considering the all the practical aspects in the simulation also, like some drop and everything, then you should get the same results in the hardware. But I cannot comment on why it is not giving. So if we provide some waveforms or something like that, then I can analyze and where the issue is in the hardware, then I can say to you. Just by hearing you, I cannot comment on that one actually.
Sir, in last lecture, I asked you that if we are considering to practically build the buck converter, what we should consider for building it. So can you tell that, because what I am doing actually is I'm just going through the data sheets of the component and applying it over there. It's not doing the proper calculation. Or should I do the proper calculations for that first and then go for the data sheets of the components?
See, majorly, one thing is that what input voltage and output for the device point of view. Okay, you can take the for the just for the practical aspect, or the for the to get the implement the hardware. You can use the higher voltage and higher current switches directly. Okay, so there is the one thing, but maybe the problem is that the whatever gate pulses you are giving, so it is not able to drive the your switch. So that can be the maybe the problem. Okay, that is the one problem.
Okay, sir.
uh, Other things like a inductor capacitor design and everything, so that will depends on the, so you will if you are not using a correct capacitor, then the you will get the higher ripple at the output. If you are not using the correct inductor, lower inductor, then you may get the discontinuous conduction, not the continuous conduction, but you should get the output. Okay, but as you said, you are not getting output, means there may be the possibility that switch is not getting turned on or turned off by the whatever gate pulses you are giving. Now how you are giving the gate pulses and what is the requirement of that switch gate pulse, so that we have to see. So even though generally means in the when we design any power electronics, we will have the one controller. So again, I will share my screen to draw something. Okay, so suppose this is the switch. I want to uh,
So your screen is not visible.
oh, sorry, I have not shared. Sorry. Now is it visible?
Yes, sir.
Okay, this switch I am using. Okay, and I want to switch on and switch off this switch. So I have to give some gate pulses like this, on and off, right? But if
Yes,
I
sir.
want to have these pulses, I cannot give the pulses from the some of the controller, which I have controller or function generator I am using, and that whatever pulses I directly I cannot give here. We will be requiring some, here it is called as the gate driver. So what it will do,
Okay.
so whatever signals you are getting, some I have the some controller which will give the voltage or the pulses in the range of 3 volt only. Okay, only 3 volt. But
Okay.
if I use the IGBT here, I will be requiring for turning on, I will be requiring the 15 volt here, and turning off, I will be requiring the minus 7 volt. So I cannot give the controller signal directly to the IGBT. I have to one gate driver which will convert this signal to the this level, and that signal can be given to the IGBT. Then only my IGBT will turn on or off. So you go to the data sheet and you see the how the what is the gate requirement. Even not only the voltage range, some current also required. Your converter will be giving the microampere current only. Okay, but here we will be requiring some amperes of current to drive the IGBT. So who will provide that one? So this gate driver has to provide that current actually.
Okay, sir.
So there will be the in between the gate driver circuitry if you are using the high power switches. There are some very low power switches are there which can directly be the derived by from the converter or the controller. And if I take the MOSFET of a 15 volt or 20 volt MOSFET, which will have the gate threshold of say 2 point or the 1.8 volt. Okay, so in that case, if I give the 3 volt signal, so it can turn on and off, but not the MOSFET which will have the threshold voltage of 5 volt or 10 volt threshold. Threshold means above that voltage only it will turn on, and below that voltage it will turn off. That is the threshold voltage of MOSFET. So that you have to go and check in the that data sheet. What is the threshold voltage of that, and what is the current requirement? And then you see whatever your gate pulse generation is there. So that is able to give that much voltage level and the current.
Okay, sir.
For gate driver, we need to check data sheet for gate current of that switch.
Yes,
And nowadays, those gate driver ICs are available.
gate driver ICs are available. Yes.
Earlier, it were on PCB like optocouplers they were using.
Yeah, we have to use the transistor and optocoupler for the isolation actually, and to
Ah,
boost the voltage and level and transistor and everything was used in previous days. But now all are coming with a gate driver ICs, which will give the whatever requirements are there. So yeah, that's true.
Sir, means what is difference between just using an gate driver IC and octocoupler? Means which is better one option if you are designing a power electronics device? Means for drivers like something motor drivers and all.
Uh, Only optocoupler again will not able to boost or change the voltage level. Optocoupler is for the isolation purpose. Actually, what will happen, I will just again draw the one thing. Why we require the isolation, that just I will clarify. So this is the one leg converter. Okay, we have suppose here 800 volt uh, DC link voltage. From that we are generating a 230 volt AC supply. Okay, are you getting?
So yes, sir.
Okay, so in that case, just I have shown one phase where we were using the two switches here, and it is giving. Now, if you see the gate pulse of this one, so this gate pulse will be given with respect to this point. Okay,
Yes.
gate pulse we have to give with respect to this point, and for this we have to give the gate pulse with respect to this point. Okay, so what is happening? So this point and this point are not same. Here you have the 0 volt, then here this point is almost 400 volt potential difference.
Yes.
Okay, and again this are sitting on the 400 volt, and your controller which is of 3 volt only, the power supply of the controller where you are generating the gate signal. Okay, so this is the at the 3 volt. So if I connect this to the directly this, so this will directly blast the your controller board. So we cannot give the gate signal directly from the controller to the this of high voltage also. So in that case, what we will be requiring the isolation between the this. Now again isolation we can have the transformer. So pulse transformer you can use, or you can use the optocoupler. So optocoupler will have the like this sorry diode here, and it will generate, and then you will get the opto isolation. Okay, so in that case this part and this part will get isolated here. Even this part will get isolated, which has the different voltage levels. Now the ICs are coming, which will have the internal this whatever optocoupler or whatever you require. So it will have the that isolation inside itself. So you will get the 3 volt PWM here. Whatever voltage level you require, say 15 volt voltage level is required. So that you will get here with a isolation. So they are isolated already. Now, if I want to replicate this with a transistor or the optocoupler, then I require a first optocoupler here, okay, to isolate it. Then some transistors and transistor or the other circuitry or the op amps to boost the voltage from this 3 volt to 15 volt or the current strengthening, right? All these things are now already implemented or the integrated into one a single chip.
Okay, sir.
So we don't require to have all these things outside. Directly we will have the chip which will give the all that things. Clear? But as of now, I don't think to, or I don't ask you to use the gate driver ICs. Instead of that, you can use the transistor and that things where you don't require any isolation things actually. You will not operate at the 400 volt or 500 volt or that kind of thing. So there you can try other things as well. But if you require the isolation and all that kind of things for the higher power, higher voltages, then you have to go for the all uh, uh, gate driver ICs.
Okay, sir. Clear now.
Yeah. Anything else
No, sir.
from others?
Sir,
Hello.
hello.
Yeah.
Sir, what are the knowledge required for the any industry in power electronics
In see, it will
for
again
placement purpose?
uh, for campus purpose.
Yes, sir.
See, industry when comes to the campus, they also know that you are the from the academic. So what kind of syllabus and everything is required. So whatever in syllabus is there, all the converter and operation of that converters should be clear. They will ask the operation, practical implementation and everything. Mostly the industry will not accept at this stage. Of course, this knowledge is required, but that will be acquired once you enter into the industry. At industry level, at least we should be clear with the basics, the operation of the all the converters. Either it is DC to AC converter, AC to DC converter, whatever converters are there, how they are operating, how bucking is happening, how boosting is happening, all that kind of things you should clear. Then comes as a practical knowledge, which is comes once you enter into the industry, you will get that one.
Okay, sir.
Even some kind of we can say the control things, how we can control. So like a miss to control the output voltage, we can vary the duty, we can vary the frequency. Similarly, if I consider the we can say the DC to AC inverter. So there are different PWM techniques, sine triangular PWM, sawtooth sine triangular, then selective harmonics, all that kind of 120-degree conduction, 180-degree conduction, all that kind of things, basic things are there for the any inverter, which is mostly will be covered in your syllabus, and that knowledge you should have.
Beyond the syllabus, what are the things need to be?
Beyond syllabus, if you have the add-on, you can do a one some good project. Okay, if I say. And when you go for the interview, try to show that as a your competency, or the you can project that what you have did. But in that case, you should have the thorough knowledge of the your project, means how you are done, how you have selected the switches, how you have selected the gate driver, how you have selected the all the components for that. All that kind of things you have to thoroughly do in that project. Do a small project, just a buck converter, but do it as a thoroughly, and then that you can project at the interviewer. So that will be the good things you will get actually. Otherwise, as such, no one will ask in the depth information of the any of the this power converter at this stage to you. So if you have this one, it's well and good. So that will be the plus point only. But the knowledge then the comes as a this only. So how you have to select the switches, what are the different things are going on in the switch point of view. Means say which material is used in the semiconductor, silicon, silicon carbide, gallium nitride. What is the what advantages we will use if I use the SiC MOSFET as compared to the silicon MOSFET as compared to the silicon carbide MOSFET. All that are some advanced knowledge we can say. If you get that knowledge, then it is very much a good thing actually. But
Okay, sir.
whatever I said as a interview, what I expect from you, if I go for the any taking the interview, and if I ask me to ask the question, so I will be more focused first on the basics. So all kind of basics which will be covered in your syllabus, and then I will, if you have done the any power electronics projects, then if you have done, even though if you have done the simulation, so I will ask in deeper in the that project only.
Yes,
So this is my point of view. Maybe you will find something different at the different things, because again it will varies person to person. But as a industry, or where you are coming from that, so I have some criteria, so I will focus on that only. Everything is
yes,
move around the basics. So basics should be clear actually. If you have the clear basics, you can do anything.
yes, sir.
Anything anything won't go beyond basics actually. If you are not able to explain the how buck converter operates, you will say only buck converter is a step down converter which will convert the higher voltage to the lower voltage. So that is not the technical answer for the buck converter. You should explain the how it is stepping down the voltage, working of the buck converter. So that you should know. Yeah, anything else, anyone else?
Sir,
Yes.
which topic is important in power electronics for gate examination or overall gate exam? How should we
Mm,
study?
Actually, recent gate exam, I have not went through the syllabus, but again, for the gate, actually, more it will be for the power electronics point of view. Miss, when I was giving the gate, that time the more was the device point of view, characteristics of the device and all that kind of thing. So that was the more important, and then the inverter was the one more important topic.
Okay, sir.
But now the recent things I don't know. frankly speaking.
It is still same scenario. Power semiconductor devices is the more important topic in gate point of view,
Hmm.
and as you mentioned, inverter, same
Yeah.
scenario.
Okay. Yeah. So I am still right.
Yes.
Okay. If there are no further question, then we can conclude today's session as well and our lecture series. But of course, if you have any doubt and anything, you can just reach out to me through the Vishal sir. If you have, if Vishal sir is also there, so he is also good knowledge of the power electronics. But anything industry point of view or anything is required, so I am here ready to help you. Very industry or practical point of view.
Yes, sir. You are always there for us. And in the conclusion part, we would like to take some feedbacks from the students. Overall, 3 sessions over 3 days. Since last 3 days, we are here. So I invite a few feedbacks from the students. Just a comments. You can have feedback about these sessions, organization of these sessions, and uh, delivery by sir. So you can have feedback. Voluntarily, students can unmute themselves and give away their comments.
Hello, sir. Am I audible?
Yes, you are audible. Yes.
Sir, first of all, I would like to thank Vishal sir and electrical department because they are doing giving their more efforts for us because lecture from an industrial expert will aware us what is required in the industry and all. And sir, your lectures were means amazing. Like we got the proper knowledge then how to implement anything and majorly if I am doing any project in practical implementation, your suggestions will always help me nowadays. Means I will come overcome my mistakes what I am doing in my practical implementations. Thank you, sir. Thank you so much.
Yeah. Thank you.
Okay, one more from boys.
It looks that miss or feedback also they are not that much interactive. Miss either I have not given a good lectures or the students have not liked this one. Just one thing, Vishal sir, you can have the anonymous feedback as well, where they can give the some whatever feedback they want and whatever corrections or the improvements are required from my side. I will try to improve it. Of course, I am also a human being, so no one is perfect in world. So I also do some mistakes or some improvements are required in my also. So yeah, that also you can also take.
Surely, sir, I'll do that. Actually, feedback form is ready. Students have to fill up their feedback compulsory on that Google form. That is ready. I'll share with uh, you as well.
Yeah,
It's
without
uh,
name, you can just share to me so that I will just try to, if any improvements are required, so I will try to do that in myself.
yes, it is. By tomorrow, I will share with you their
Mhm.
response
So
as an
feel free. It's my humble request to everyone. So please give the uh, uh, Miss what we can say, the true feedback, whatever you feel, or whatever things are good, whatever things were bad, where improvements are required, all that kind of things you can write. So that will be actually one good feedback to me. So I will try to improve myself with that feedback.
Okay, one boy. Anyone from boys? Atharo Patil, are you there?
Yes, sir.
Hmm.
Yes, sir.
There are two Atharo Patils. Both of you can.
Sir, overall lecture and everything was nice. Every Each and every point was really informative for all of us. And I don't think that there is any a question that will arise in us after the lectures.
Thank you.
Okay, from girls, Shravani Patil. Or anyone else who is there now.
Sir, in 3 days lecture of series, the information you given is very good and informative to exam point of view, and the knowledge we gain to give us, and it is a very informative lectures. Thank you.
Thank you.
Anyone else?
Sir, thank you for the 3 day session. It was very informative. Basic concepts were clear, and uh, overall everything was nice.
Okay. Thank you everyone listening me to for these 3 days. Actually, online lecture is not so simple to hear all this kind. Uh, 2 hours lectures attending online is very difficult. I know that one. If it would have offline, so you will have thought of how the time went. But online time and always keeping the concentration at the lectures is very difficult. But all of you have attended all this lecture for the whole time, and whatever I wanted to deliver, so you listened carefully. So thank you for that. Thank you everyone.
Okay, in the last, to conclude the sessions, I am here to say big thank you to Dr. Mahendra Ghat, sir. I'm really grateful to you, sir, for accepting our invitation and sparing so much of time from your busy schedule. Uh, Throughout these sessions, uh, last year also we had a session, but those sessions were hybrid, I mean offline as well as online. Now for this year, we went completely online, and as you mentioned, it is really difficult to maintain focus during online lectures for students as well as the uh, s- speaker or presenter or resource person.
Yeah.
Through these sessions, I'm uh, to the conclusion that you are really passionate about your teaching. You are really source of motivation for our students. We will invite you for our next course, electrical drives, where also we you have your expertise. That time we'll try to have that offline. Apart from that, you are always welcome in the campus of RIT. not necessary that there are lectures planned or not, you are there. I need to mention here, sir is from our part of state, just 25 kilometers away from us. His native is Dudgaon, that is Kolhapur district, and boundary of Sangli and
It's Sangli district
Kolhapur.
only.
Sangli district, yes, Sangli district, in the basin of Varna River. And that's why we really feel proud of you, sir, for your achievements, because you took your bachelor's from Walchand College and then went for your MTech from NIT Warangal and then completing PhD at IIT Bombay. It is really wonderful journey, as well as why we are really proud of you, because you are ex-employee of RIT. So we always in the touch of excellence. That's why we are in the relation as a ex-employee. You are from RIT, so I need to appreciate your efforts, your commitment towards delivering the lecture exactly, joining on the time, and 2+ hours that you are dedicating for us. And you have almost like motivated as well as inspired our students to ask their queries and answer their queries uh, during your sessions. And in the final session, as you mentioned, how to prepare for the campus interviews, because being a technical institute, it is really important to have that side of thing is very important. That is how to prepare for uh, placements through our course. And I would like to mention here, most of the interviewers, though they are from core or core electrical or not, they are really interested in the power electronics, and they really know something about it, and they purposely ask questions related to power electronics. And that's why this becomes really important to prepare for basics, as you mentioned. At least you know the basics. Just giving the significance, or just giving the purpose of that particular device, you can explain how that device works. That was really spot on. That is how a student should prepare for their interviews. As well as get also, you mentioned which topic is important, and very importantly the converter topology. You are uh, above level as far as the explanation and everything, the way you prepared. And that's why I mentioned that you are passionate about, you are first as a teacher, and then you are part of industry now. So keep us motivating and keep us enlightening. I hope you will accept your our uh, next invitation as well for course of electrical drives. So on behalf of Department of Electrical Engineering, Rajaram Babu Institute of Technology, and student fraternity, I would like to say a big thank you to Dr. Mahendra Ghat sir. I also appreciate the efforts of my students being there for 2 hours and joining on time, and those they are really active during their sessions. I really thank for them. And here I conclude, the sessions are over. Thank you so much, sir.
Thank you for this kind words, and also giving this opportunity me to present or the give deliver the lectures. Thank you to you first, and also to the HOD and the electrical department.
Thank you, sir.
And
So
big thank you to the all the students to listening me.
Thank you, sir.
Thank you. Okay, then see you again.
see you. Good night, everyone.
Good night.
Yes, sir.